Good day, everyone, and thank you for being here today. The topic of our discussion is Introduction to Time Series Analysis, presented by the Full Academy. In this session, we will explore the fundamental aspect of time series analysis, starting with the basic definitions and working through key concepts, models, and practical examples. By the end of this presentation, I hope you will understand how time series is structured, analyzed, and used for predictions. Let's start with some basics time series. To begin, let's define what we mean by a time series. A time series is a sequence of data points indexed in a time order. It involves observing a particular variable such as temperature or stock prices at a regular time interval. This could be daily, monthly, or even yearly observations. Time series analysis aims to understand how this data evolves over time and ultimately to make predictions based on past observations. In many ways, time series analysis extends the concept of linear regression, but with the important difference. We assume that data point depends on previous values. In other words, while linear regression assumes independence between variables, time series analysis embraces that today's data is often related to yesterday's data. This temporal dependency is the key element that distinguishes time series analysis from other statistical methods. Now, let's consider a simple example to illustrate this. Suppose we want to predict the daily average temperature in a city like London. In a time series analysis, we use past values, such as temperatures on previous days, to predict future values. This difference from standard linear regressions, where we assume that independent variables like population and elevations affect temperatures. In time series, the assumption is that yesterday's temperature and the days and before that influence today's and tomorrow's temperature. This dependency over time makes time series analysis such a powerful tool for forecasting, particularly in fields where past data patterns are expected to persist in the future. When analyzing a time series, there are several key characteristics we need to identify and account for. Let's go through them. First one you can see on the screen is trend. This refers to a long-term increase or decrease in the data. For example, you might see a gradual rise in the global temperatures over many years, indicating an upward trend. Seasonality, this is the regularly repeating pattern in the data, often linked to specific time intervals such as daily, weekly, yearly cycles. A classic example is the electricity demand, which tends to peak in winter due to heating needs. Outliers, these values significantly differ from the rest of the data. Random events of data record error could cause outliers, but they can substantially affect the analysis, so it is essential to identify them. Variance, this refers to how much the data fluctuates over time. Sometimes the variance is constant, which makes the data more predictable. Other times, the variance can change, which adds complexity to the analysis. Identifying this characteristic is essential for choosing suitable model and make accuracy forecast. Now let's look at our model first. The additive model, each component, trend, seasonality, and residuals is combined additively in this model. Mathematically, this can be written as xt equal to tt plus st plus wt. Xt is the observed value at time t, tt is represent the trend component, st is the seasonal component, and wt represents the residual and noise, which captures the randomness in the data. This model works well when the effects of the components are independent and the influence of overall data can be summed. In other words, the trend, seasonality, noise are separate factors that don't interact with each other. Multiplicative model. Multiplicative model is another important framework in time series analysis. It's used when the effects of the trend, seasonality, and noise are not independent, but rather interact proportionally with each other. The formula for the multiplicative model is xt equal to tt times xt times wt. In this model, the components multiply together, meaning that the effect of the model is often used when we expect the components' effects to scale with the magnitude of the data. In summary, while the additive model is useful when the components are independent, the multiplicative model is better suited when the components interact and the effects are proportional. Now, let's go talk about noise. Noise plays a crucial role in a time series analysis. Noise refers to random fluctuations in the data that cannot be explained by trend or seasonality. There are several types of noise we may encounter. The first one you can see on the screens is white noise. This is the simplest form of noise. It is a random process with a mean of 0, constant variance, and no correlations between time points. In other words, white noise is completely random with no discernible pattern. In weak white noise, the variables are uncorrelated but not necessarily independent. This means that the noise may not follow a predictable pattern, but it still doesn't influence adjacent time points. IDD white noise. This stands for independent and identically distributed noise, where the values are independent have the same probability distributions. Gaussian white noise. This is a specific type of white noise where the distribution is normal or Gaussian. It is most commonly assumed type of noise in many models because it's well understood statistical properties. Understand the type of noise present in the time series is crucial for accurate modeling and forecasting. To wrap up this session, let's summarize the basic objectives of the time series analysis. The first goal is to identify and describe the key characteristics of the data, whether it's trend, seasonality, or noise we discussed earlier. We want to understand how past value influence future ones, which helps us develop models that can accurately forecast the future. A major objective of time series analysis is prediction. We aim to make informed predictions about future values based on the historical data. Finally, in the industrial applications, time series analysis can be used to monitor processes and ensure quality control. For example, in manufacturing, we can track a production's quality over time to identify any deviations or trends that require intervention. By considering these objectives, we can apply time series analysis to various fields, from finance to climate science, and achieve meaningful insights from temporal data. Let's look at some data. In this slide, we present with the data showing my daily commuting time over the past 100 days. We are looking for any potential patterns and trends in these patterns. Is there a consistent increase or decrease? Do we see spikes in the data that indicate an outliner? This plot is straightforward example of how time series data can be collected and analyzed in real life. A commuting time series could help us predict future commuting times based on the past, allowing for better planning and time management. In this slide here, we represent a lab plot of the same daily commuting time data we saw previously. In a lab plot, we compare each value in the series to the previous one. In this case, the lab plot shows a positive linear association, meaning that if my computing time was extended on one day, it would likely be long on the next day. This suggests that the commuting time are correlated over time, which is common in many time series. This also implies that we can use correlations to forecast future commuting times. Let's dive deeper into analysis my daily commuting time. We use regression model without accounting for trends or seasonal patterns for this data. The analysis showed no consistent trend over time, meaning there wasn't a general increase or decrease in commuting time. Additionally, there are no significant seasonal patterns, such as a larger or longer commutes on specific weekdays. However, the lab plot reveals a positive linear association, which we just discussed. This suggests that the past commuting time predict future values, meaning that this data might be suitable for time series forecasting models. Let's look at another example. This slide shifts to new data, quarterly beer productions in Australia over 18 years. The graph shows a clear upward trend indicating that beer productions have generally declined. However, we also observe a significant seasonality as beer productions appears to peak at irregular intervals. These could be due to seasonal demand with a higher output during the specific times of the year, such as summer and holiday seasons. This dataset is an excellent example of how time series analysis can reveal both trends and seasonal patterns that can be used to inform business decisions. Finally, let's analyze the beer production data in more detail. We applied a regression model for this dataset to include trends and seasonal patterns. The results show an upward trend over 18 years, suggests that beer production has increased. The trend also indicates some curvatures, means that the increase is not perfectly linear, but might accelerate or decelerate over time. The analysis also finds significant seasonal effects. In other words, beer productions trends to peak during the certain times of year, and likely due to increased demand during particular seasons or holidays. Overall, the model used here including both quadratic trend and seasonal effects, which provides a good fit for the data and helps understand the underlying patterns. Let's look at some popular models in time series data analysis. First model we can see here is called optoregressive model. In the short form, we call it AR models. An optoregressive model assumes that the current value of the time series xt depends linearly on its past values and error term. The general formula for an optoregressive process of order h or ARH is as follows: xt equal to delta plus find 1 xt minus 1 plus find 2 xt minus 2 plus so on until to the let term h, as you've seen, is phi h times xt minus h plus wt. Each variables can be represented as follows. Xt is the value of the time series at time t, phi 1, phi 2, phi h are the optoregressive coefficients, wt is the white noise or error terms, and h represent the number of lag terms used. This model works well when we believe that the current value of the time series is influenced by the several past values. Next one you can see is moving average MA models. We have MA models where the current value xt is expressed as the weighted sum of the past white noise terms. This model helps smooth out fluctuations in the data. The general form of the moving average model, RQ or MEQ, is xt equal to a summation size starting from j equal to 1 up to q, And then you can see the form is theta j times wt minus j plus wt. In this model, you can see that theta 1, theta 2, theta q are the moving average coefficients, wt is the white noise, and xt is the average of time series at time t. Moving average models are useful for filtering out the short-term fluctuations and for creating the smoother predictions. For instance, we use the moving average to smooth out noisy stock prices or daily COVID-19 case counts. Finally, we come to linear process, which provide a general framework for modeling time series. Both AR and MA models can be considered special cases for linear process. The general form of linear process, and you're just going to combine AR and MR models together. This equation represents linear combination of past value of the time series and white noise term. Linear process can capture complex dynamics in time series data by flexibly combining optoregressive and moving average components. In conclusions, time series analysis extends classical statistics to account for temporal dependencies. Understanding noise, optoregressive, AR, and moving average MA model is crucial for building predictive model. We have discussed the several models such as the additive and multiplicative models and AR and MA processes, all of which helps explain and forecast time series data. This concept has broadly application from predicting stock prices to understand climate pattern. Thank you for your understanding and attention, and I hope this introduction has given you a strong foundation for exploring the time series analysis further. Thank you.